Hello students, in this section 1 we are going to be considering the basic introduction to uniform circular motion. So I'm going to walk you through the slides and I'd like you to intermittently pause the video so as to be able to absorb every tip, every hint, every concept and so on. So let's get started. I'll walk you through the slide. Please feel free to pause the video and then go through the formulas. This is the formula preview. This is the next one. Go through the formulas. Okay, hints, tips, definition of terms. Go through every point here. The difference between circular motion and rotational motion. Please, I'd like you to take note of the 3 points. They are very vital. Okay. All right, so let's answer this question. It's part of the introduction. Centripetal acceleration is given as omega squared r. Proves this. Okay, so let me divide my board into 2. Okay, let me divide this board into 2 like this. All right, I need you to recall that centripetal acceleration is equal to v squared all over r. You already know this one. Again, note that v is equal to omega r. All right, I think we had already proven this before. Now, if you plug in this value into this, definitely you're gonna get AC is equal to omega r all squared all over r, and of course it will give you omega squared r. Very simple. But how do we also show that a centripetal acceleration is also given as 4 times pi squared times r all over period squared? Again, note that v is equal to distance all over time. That's by definition. Of course, if we are calling v speed, that's distance over time. If we are calling v velocity, that's displacement over time. It doesn't matter. Sometimes we model them up. Okay, but if we are considering a circular path, this is a circular path, and this is the center. If an object starts from this point and then moves around the circular path and arrives at the starting point, this object definitely will have made one complete cycle or oscillation. Okay, and the path taken is the circumference of this circle. So S will be 2 pi r. That's the circumference of a circle. And time will be period. That is time over one cycle is period. Remember that period is the time taken to make one complete oscillation or cycle. All right, so if we plug these 2 parameters into this, we are going to get, we have v is equal to 2 pi r all over period. Now, if you substitute the value of v here into the main equation here, you are going to get that AC is equal to 4 pi squared r all over t squared. Very simple. And of course, if you get centripetal acceleration, definitely you have gotten centripetal force, because centripetal force is equal to mass times centripetal acceleration. So that is it for this slide. Next, we are asked to show that distance is equal to angular displacement times r. That's linear distance or linear displacement is equal to angular displacement times r. And velocity or speed or linear velocity is equal to angular velocity times r. And then a, that's linear acceleration, is equal to angular acceleration, times r. Alright, so let me divide this board as usual and then pick my white pen. Now, we don't really need to pay heed to this and to this. Once you know the first one, that's S, is equal to this times R, and you divide both sides by T. Divide both sides by T. Take note of this. This is what? This is our V. And this is what? This is our angular omega, or angular velocity. Then you have got what? You have got that V is equal to omega R. Again, if you also divide through, if you divide the left hand side and the right hand side by T, divide through by T, divide through by T. Please, can you recognize this? This is what? Linear acceleration, and this one is angular acceleration, like this. Of course, you have got what? That linear acceleration is equal to angular acceleration times R. Very simple. Okay. Now, how do we now prove that S? Because that's the bone of contention here. How do we prove that S is equal to theta times R? Okay, so let me divide my board as usual. Now, if this is a circular path, this is the center of the circle. Okay, if an object moves from this point, let's say point A, to this point, point B, remember this is the radius R, and then this is the radius R. The angular displacement will be theta. Okay, and the distance swept through, let's call it S. Let's call it S. All right, that is the linear displacement, okay, or the arc AB. Now, okay, so if we equate this, if R becomes equal to S, then theta will be equal to 1 rad. Of course, we can redraw the circle like this and have this 1 rad if R becomes the same as here. Now, if we take the ratio of theta, the angular displacement, and equate it to that of the angular displacement, sorry, the linear displacement, or AB, which we have also called S, then we'll get that theta all over 360 degrees is equal to S all over 2 pi R. Yes, because AB is part of the circumference. So S all over 2 pi R. Now remember that theta will become, this theta will become 1 rad. And once that happens, that means that S will be the same as R. So that if R cancels R here, then we'll be left with what? 2 pi rad is equal to 360 degrees. You must have, come across this relationship between radian and degrees. That's how to go from radian to degree. Okay, but this is not what we are driving at. We want to prove that S is equal to theta times R. Now let me go ahead and redraw the circle. Okay, the same thing. We have the center. Okay, this object moves from here to here. This is A and this is B. This is my S and this is the angular displacement. Okay, let's do the same thing we did before by taking the ratios. We have theta all over 360 degrees is equal to S over 2 pi R. Next slide. Again, let me divide this. I think this is the final one. All right. Now, we had the previous slide. We had theta all over 360 degrees is equal to s all over 2 pi r. But of course, we noted that 2 pi rad is equal to 360 degrees. So we can replace this with 2 pi rad. And that will give us what? That will give us theta over 360 degrees. Oh, sorry. Let me erase this. That will give us theta over 2 pi rad is equal to s over 2 pi r. Okay? And of course, this takes care of this, And then we'll now be left with what? We'll be left with theta all over 1 rad is equal to s over what? Over r. Therefore, we can see clearly that theta is equal to s over r. Of course, the unit will be rad. Since the linear displacement is cm and radius, of course, is cm, the two cm's will cancel and then you'll be left with rad. So that is it. So when are these possible? When can we equate centripetal force to frictional force? Of course, I hope you remember. Let me divide this. Oh, I'm not seeing what's going on. Okay, so let me divide my board. Remember that frictional force is equal to the coefficient of limiting or static friction times normal force or the normal reaction. All right, so if a car moves round a roundabout, what supplies the centripetal force to the car is friction between the tires and the tarred road. So we can now equate this to this. Now, if an object moves around, for instance, the planets, right, move around the sun. Let's take the Earth, for instance. What supplies the centripetal force to the Earth while it is moving around the sun? It is the gravitational force of the sun. All right, that's what supplies the centripetal force. So we can equate this to this. All right, if I also tie a rope to a stone, if I tie a stone to a rope, whichever way, all right, and then have it wired either horizontally or vertically, what supplies centripetal acceleration to the stone? What keeps it moving around the circular path? It is the tension in the rope, the tension in the rope. That's what supplies the centripetal force. So we can equate the centripetal force to the tension, either tension in the rope or your hand if you are the one whirling it. Is that okay? All right. So know what supplies the centripetal acceleration or centripetal force at every point in time. This should be the final question. What is the major difference between circular motion and rotational motion? Please take note of this phrase, axis of rotation. All right, axis of rotation. Now, if the axis of rotation is outside the body, okay, I have the central position here at the center, and then I have this body, okay, move around this circular path like this, okay, with the center or the fixed point or the axis of rotation outside of the body. This body is said to be undergoing circular motion. But if I have the same body like this, and then this fixed point here is located within the body itself, and this body spins or rotates, then we can say the body is undergoing rotational motion. So the key difference between circular motion and rotational motion is actually this word, axis of rotation. If it is outside of the body, it is circular motion. If it is within the body, then it is rotational motion.